Okay, so in the previous video, we talked about how to perform indefinite integrals, right? Where basically we're trying to find the antiderivative of a function. So to recap, if we take the integral of f of x dx, right, we're finding a function, capital F of x, right, such that df over dx, right, so such that df over dx is f of x. Okay, so we covered a few examples previously, and that was how to take the integral algebraically. If I give you an algebraic expression, how do you find the integral of this algebraic expression? Now let's talk about the geometric intuition. In most of physics and math, it's very important when you study a concept to have both a geometric feel for it as well as a algebraic understanding of how to perform the calculations. So let me just go back a little bit further, right? Previously we talked about the derivative, and specifically we saw that for the y equals to x squared function, right, if we take the derivative, then the derivative looks something like that. The derivative function looks something like that, and the derivative is 2x. And the geometrical intuition for the derivative of a function is the gradient of the function. So for example, if I pick this point over here at, let's say, x equals to 1, I'm asking the derivative function tells me what is the gradient at this point x equals to 1. So I'm drawing a tangent line to it, and you see that this tangent line has a gradient of 2. So that implies that this derivative function has a value of 2 at x equals to 1. Okay, so this gradient is equals to 2. So that's the geometrical understanding of the derivative. Now, what's the geometric intuition for the integral? It turns out it's the area under the graph. So if let's say I plot, I'm going to plot y equals to x for a simple example. And if I want to find the area under the graph for, let's say, x equals to 1 to x equals to 3, right, we can see that for this linear graph, it is easy to calculate the area under the graph because the area under the graph is just the area of this trapezium. And we know the area of the trapezium is just half times height times base plus the base. So in this case, the area is just half times 3 minus 1 times the height over here. The sum of the two heights here, which is 1 plus 3. And this gives me 4. This is easy because the graph is linear, so any area under the graph will be a trapezium. However, if we talk about non-linear graphs like y equals to x squared or y equals to x cubed, then the area under the graph in general will not be a trapezium. It will not be a nice shape for us to apply some formula to, and the area under the graph would need to be calculated using a definite integral. So I'll first present to you how to calculate the area under the graph of this graph using integration to show you that it works, right? You get the same answer as if you apply the trapezium formula. And then after that, I'll generalize this notion and talk about how you find the area under a graph for a general could be non-linear function. So the area under a graph, right, is just the integral. And now we write the integral sign with the two, we call it limits of integration, the two endpoints that we want to integrate from one endpoint to another. So this means that we're integrating from x equals to a to x equals to b, where a is the left hand side, right? This is x equals to a, and the right hand side is x equals to b. For now, we want a to be less than b, right? If not, we have to actually apply it's actually a negative of, if we flip the a and b, right, then the integral will pick up negative sign. So yeah, so the integral of this with respect to dx, after you get that, right, you get this. You get f of x plus c, where c is arbitrary constant. And then when we perform the definite integral, instead of just leaving the answer at f of x plus c, we substitute the two endpoints of this function with x equals to a and x equals to b. And we take the difference. So we take f of x plus c evaluated at x equals to b minus f of x plus c evaluated at x equals to a. So what we get is that we get f of b plus c minus f of a plus c, and we see that the constants cancel out, and we get f of b minus f of a. So what this means is that, suppose I have this graph over here. This graph is f of x equals to x. If I integrate x with respect to dx from 1 to 3, this should, by the principle I just described here, this definite integral should give me the area under the graph of y equals to x, right, which is this graph that I plotted over here. It should give me the area under the graph from x equals to 1 to x equals to 3, which is what I calculated previously using the trapezium rule. But now, instead of using the trapezium formula, right, I want to calculate it using a definite integral, and I'll show you that I get the same answer. So this is the integral of x is half x squared, right? And half x squared, don't forget the plus c. And I'm not done yet, because if I were to perform the indefinite integral without these limits of integration, without the two endpoints, then this will be my answer. But because I have these two endpoints over here, I need to substitute the two endpoints into the function, and I usually denote it as this, right? Or even to be more precise, to be more clear, I'll write this. So I'm evaluating this function at these two endpoints, and I'm taking the difference of the result. So this will be half of 3 squared plus c. This is evaluating it here, minus half of 1 squared plus c, which is evaluating it here. And I'm taking a difference of these two values. So this is half of 9. So this is 9 over 2 plus c minus, this is 1 over 2, and this one minus c. So the c's cancelled out, right? And in the end, I get 8 over 2, which is 4. You can see that that coincides with our trapezium formula over there. But the trapezium formula is unable to generalize to non-linear graphs, whereas the integral is the correct generalization to non-linear graphs. So the integral allows us to calculate the area under a graph, right, for any function f of x. So yeah, that's cool. And there's a few reasons why we want to perform integrals. Number one is when we talk about physics, right? Often in physics, the equations will give you the velocity of a particle with respect to time. And if I give you the velocity, right, it tells you how fast the particle is moving at each point in time, right? So perhaps it's moving here very fast, and it speeds up, so it gets faster and faster. And from this information, I want to obtain where the location of the particle is. And mathematically, right, this will correspond to just performing the integral, because the derivative of position is by definition velocity. So if I perform the integral of both sides of this equation, then this will give me x of t plus c. So that's one reason that's one reason why when I study integrals, is that if I give you some information, I want you to derive other kinds of information. And when the information are linked together by a derivative, and I give you this information to get x, right? To undo the differentiation, you need to perform an integral. Another reason for that, so that's kind of talking about why we need to do indefinite integration, right? But how about for definite integration? For definite integration, so once again, this is indefinite. For definite integration, the reason why we want to do definite integration is because indefinite integration is the area under a graph. And roughly speaking, right, the area under a graph is a sum of many small rectangles. It's a sum of many small rectangles. So usually when we perform a sum in physics, right? So for example, if I have a massive body, right? Some blob of mass, and I want to calculate the sum. Perhaps each mass contributes each small piece of mass contributes a certain amount to. In future, we're going to learn this, but it contributes a certain amount to the moment of inertia. And the amount that it contributes is a non-linear function of its location. So for example, if this is the origin, and the small piece of mass is a distance r away from the origin, then sum over the masses of m of r half m r squared, right? So m of r is a function of r, telling me how massive this blob is. If I want to perform this sum, right, this sum turns out to be equals to the integral of dm of r squared. So we write this as r squared dm. And this is known as the moment of inertia of an object. So in other words, this example doesn't seem very clear right now. It's because we haven't studied rotational dynamics. But when it comes to rotational dynamics, it will turn out that we need to perform such so-called infinite sums. And when we want to perform infinite sums, right, the way to do it is we perform an integral. So the integral is kind of thought of as a continuous infinite sum, and it generalizes the notion of summing many small parts. So that's the idea behind definite integration and its application to physics. So now before we go, right, let's ask a question. Why do we not see the arbitrary constant c appear in the formula for the area under the graph? And the reason is just because that it cancels. But can you imagine this graphically? Can you imagine what this is saying? What this cancellation is saying graphically? So the answer is that when we imagine the area under a graph, right? So let's say I have y equals to x, and we know that the integral of y equals to x is half x squared. So half x squared kind of looks like that. This is half x squared, and this is this integral of x dx. But we know that when we perform the antiderivative, right, we have a degree of freedom, right, which is the constant that we plug in. So in other words, if we translate the function up, so for example, this is half x squared plus, let's say, 3, right? Then half x squared plus 3 is still a valid indefinite integral of y equals to x. And any amount that we translate it out by, right, if let's say we want to find the definite integral from x equals to a to x equals to b, right, remember that the definite integral of from a to b of x dx is half x squared plus c evaluated at b and a, right, taking the difference of this function at these two endpoints. So that means that I'm basically drawing a line up from these 2 points, x equals to a and x equals to b, and I'm taking the 2 endpoints, right, here and here. I'm taking the height difference of these 2 endpoints. But we saw that this function depends on c, but the final answer, the final result, doesn't depend on c. The final result is just half b squared minus half a squared. It doesn't depend on c because c cancels out. And the answer is that if no matter what constant this c is, right, because this constant c will only translate this graph up and down, right, translate every single point the fixed distance. Even if I chose a different value of c, let's say I chose c equals to 3, this height, this red height over here, right, it's the same as this orange height, right, because I translated the entire graph by a fixed amount. So algebraically, we see that it cancels out nicely, but this is the geometric reason for why why it cancels out, because adding this constant c over here, it just amounts to shifting the entire antiderivative graph up and down by a fixed constant amount, and that does not change the relative heights of the points on that graph. And when we take the area under a graph, right, when we take the indefinite integral of some function, right, it makes sense because the area under a graph, right, the area under a graph should not depend on some arbitrary constant that we chose, right? The area under a graph is some fixed quantity, and if that quantity depended on some random number that we can choose, then we can kind of assign any answer we want, and there will be multiple answers for the area under the graph which is incorrect. So that's just a side note about why this arbitrary constant c does not, it appears in the indefinite integral, but it does not appear in the definite integral. So that's it for the definite integral. And in the next lesson, let's go through some exercises.